Hi, and welcome back to this third lecture of the computer security module. In this lecture, we will discuss another class of security protocols known as the non-repudiation and anonymity protocols. Actually, there are two classes, but they are very much related to each other. Basically, one is the reverse of the other one. Okay, so we will start today with non-repudiation or non-repudiation class of protocols. Right, first of all, let's try to understand what non-repudiation means. Basically, let's first try to understand what repudiation means. And repudiation is defined as the rejection or refusal of a duty, relation, right, or privileges, according to the West's Encyclopedia of American Law. Basically, it means that you reject or deny something, that you've done something, or that you need to do something, or certain right or privilege. By contrast, non-repudiation is the exact opposite. So it basically means that you have the ability to deny a false rejection or refusal of an obligation with irrefutable evidence. Okay, so repudiation means that you deny, whereas in this case, non-repudiation essentially means that you cannot deny that you have done something, or that you have the right to do something, or that something happened, essentially. Moving on to the area which is relevant to us in the context of protocols, and we have this class of protocols known as non-repudiation protocols. Okay, so in a security protocol context, the idea of non-repudiation means that participants can collect enough evidence to prove that other parties, uh, basically participating also in the protocol, did perform certain events such as sending and receiving of messages. Okay, so we're interested here merely in these two actions only, sending of a message and receiving of a message, and that's because we are essentially working within the context of uh, communication networks and communication protocols. In addition to this kind of property, we are also sometimes interested in proving that non-repudiation protocols also exhibit fairness. Okay, so the idea of a fair non-repudiating protocol is that no agent or no participant in that protocol can reach a point where they can present the evidence or possess certain amount of evidence before the other agents have. Okay, so you cannot essentially allow an agent to present evidence unless everyone else has reached sufficient level of information or participation in the protocol such that they've also amassed similar amount of evidence, if they can, okay, to also non-repudiate certain events in the protocol. So that's in a general setup. Now, we'll try to motivate a little bit why we think that non-repudiation is important. Non-repudiation is, in fact, an essential element and an essential property of many systems and many protocols in the real world. Probably the most important area being e-voting. So the idea of that you can essentially produce an evidence that you have, voted in a certain way is very important. Also, in auditing and accountability, you also need to always be able to produce the evidence that certain events have taken place. For example, certain transactions have taken place and stuff like that. And that is, of course, the basis of all the e-commerce. The idea that you can produce some kind of receipt or of transaction or some kind of evidence that the transaction took place is a very important one, without which we can't do many of these things. Right, so remember last time we said that in any protocol setup, we have this concept of an environment or of an attacker who is sort of your general network, your public network, which is trying to always disrupt or interfere in the protocol. And we didn't talk much about it last time. We will talk more about those kind of aggressive environments, or any public environment, in fact, once we talk about attacks on protocols. But in this case, we just want to highlight that the model of the environment is different in the case of in this case of or in this class of protocols. And in this case, the environment is not one which is basically observing and attempting to interfere in the way that the protocol is run, but it's more kind of a passive or an arbitrating sort of environment. Okay, so the idea of the environment here is that it's some kind of a referee that you can present the evidence to that certain events did take place or didn't take place. Now, of course, this comes from the fact that environments are trusted. Okay, so we're using here the sense of the environment as a trusted thing, and that's effectively different from the previous cases where we talked about environment as being something which was not trusted. And in fact, in this case, it is more the participants in the protocol who are not trusting each other. Okay, so the agent A and B communicating with each other are essentially non-trusting of each other, compared to the previous setup where they were assumed to be honest entities talking, or following the steps of the protocol as is required. Okay, so if we are going to design or define a non-repudiation protocol, we have three main goals for that, or three main objectives that we want to achieve. First of all, we want the protocol to be able to create evidence. Okay, so essentially, can the agent produce some data or enough amount of data or information out of its participation in the protocol that constitutes the required evidence for that agent to hold on to once everything has completed. The second thing is the evidence itself correct? Okay, so the information that you're getting out of your participation in the protocol, is it really suitable? Or perhaps it's not suitable. So that's also something which is required. And finally, the analysis of the evidence itself. Okay, so did the agent participating in the protocol behave in accordance with the protocol or not? In other words, can you get the outcome that you require out of that evidence, or not? Or is the evidence actually pointing towards something completely irrelevant or incorrect? Now, we in sort of formalizing this, or sort of putting this into more concrete terms, we define something called the evidence event. Okay, so essentially these are like kind of a markers, or there are certain events that we insert in the definition of the protocol, just so that we know at which point we are talking about the evidence. Okay, so they represent basically events that tell us, you know, at certain points in time or at certain stages of the protocol, what kind of information have we accumulated that allows us to make certain conclusions. So the format of that is often the way we write it, is as follows. Okay, so we say that you have an evidence here for agent A, and you have evidence here for agent B, and agent A and B are the two participating agents in the protocol. And of course, the evidence itself will be different. Okay, so A will have some evidence E, whereas B will have some other evidence E prime. And what you want to essentially arrive at is this conclusion that non-repudiation for a certain agent means that the evidence that they've collected is essentially pointing or implying a certain fact. Okay, and remember we said that in this case our interest being in the context of communication protocols, our interest is about these facts is purely whether certain agents or certain entities sent or received certain messages, and that's as far as we go, simply because, as I said, we're working within the context of communication protocols, and we're not interested in other types of facts or events. Although equally, of course, if you are considering a wider scope, you would also consider other events in your when you're evaluating your evidence. So, as such, we narrow down the definition of evidence as, first of all, evidence that implies that certain messages were sent. Okay, so the idea here is that, say, for example, that sometime during the protocol, A sent a message M to B. Okay, and so in this kind of evidence, B would want to have or would like to prove that indeed A was the agent that sent message M. Okay, so this is the kind of evidence that it will want to accumulate during the course of the protocol to be able to produce it at the end, and such that that evidence will inform the rest of the world or the arbitrator or the outside environment that indeed A was the agent that sent message M. So we write that in a more formal way, or we call it in a more formal way a non-repudiation property for B. Okay, so it's a non-repudiation property for B because it's serving B. Okay, it's from B's point of view, and this non-repudiation property for B includes evidence that essentially that implies that A did send M. Okay, so we don't know what that evidence is, but that's the goal. That's B's goal, is to accumulate as much of this evidence as possible from its participation in the protocol to be able finally to conclude that A was the entity that indeed sent M. Okay, so that's what B wants to prove in a setup like this one. On the other hand, the second type of evidence that we would want to produce is evidence that implies that certain messages have been received. Okay, so in this case, again, similar to the previous setup, you have during this course of the protocol a essentially sending a message M, but in this case, the evidence that A would want to accumulate or collect out of the protocol is one which will allow it to prove that B indeed received the message M. Okay, so A wants to prove that B received message M, and we call if that implication did did hold true, we will then have proven a non-repudiation property from A's point of view, or we call it non-repudiation for A. And of course, very important rule, and this rule, as I mentioned it last time, still applies here, and it will always apply, is that any evidence, any proof you are essentially trying to um, arrive at or conclude must rely on guarantees provided by cryptography. Okay, so simply if you send me a message A, there is no proof that you sent it, nor there is any proof that I received it, unless both of us can produce enough cryptographic information that essentially show or that that message was indeed sent or received. Right, so let's take one famous example of non-repudiation protocols, the Juels-Goldman protocol, and we try to study this protocol and try to understand the concept of non-repudiation in communication networks through the eyes or through the lens of this protocol. Okay, so it's a simple protocol consisting of 4 steps, and essentially it involves agent A communicating with agent B. So they are the ones that take part in this or participate in this protocol, and they do so with the help of a trusted server or a database, let's say a database server. So the protocol starts as follows. A sends to B a message containing B's name plus some kind of a message M encrypted with a key K that A has generated locally. And then these two things, B and the encrypted message M, are signed with the private key that belongs to A. Okay, so once B receives this signed message, it can use B's public key, which corresponds to this private key here, um, to verify it or to validate the signature, and if the signature is correctly constructed, then and valid, then it will be able to conclude that indeed the whole message came from A, okay, or was signed by A. Now, of course, as we said, signature does not hide the internal content because you still have the internal message attached to your signature. So therefore, this internal content, B and the encrypted message M, are available to B. So B, all what it does here in the second message is that it takes that content and itself will sign it using its own private key KPRB. So when it performs the signature, it then sends the whole signed message back to A, and A, of course, naturally will look in the public directory for B's public key called KPBB, and it will use that public key to validate this signature. And if the signature was constructed in a valid way, then it will be able to also extract the internal content and arrive at the conclusion that the whole message indeed came from none other than B themselves. Okay, so a couple of messages initially just so that A and B prove to each other that they're talking with each other, and there is some information that they've exchanged within that talk. Now, once A receives the second message, it then constructs this third message as follows. It takes B's name and the key K, and it basically signs those two elements and sends them to the server. Okay. Now, once the server receives this message, it knows that that it came from A because it was signed by A. And finally, it will. So once it receives this message, it will then deposit this key K in its own internal database. Now, at this point, there are two events that can happen in parallel. And that's why I said it's a four-way handshake and not a five-way handshake, because really these two events are just one event that can happen in parallel towards either A or B. And what these two events are they're basically the downloading of the key K from that server. Okay, so the server can download the key K to A through a message which is signed by the server. Okay, so you know that the key is coming from the server, and similarly, it can do the same thing towards B. So B can also download the key K from the server in a trusted message signed by the server itself. Now, of course, that key is accompanied by the names of A and B, meaning that this key is intended for communication between A and B, or the purpose of this key is that it can be used for communications between A and B later on, if A and B would like to exchange any sort of hidden messages or sensitive messages and so on. Okay, so the idea here, you perform three or couple of let's say a couple of signed messages here, just to prove to the other party who you are, and then A deposits the key in the server, and then finally in the last step the server can distribute the key to either A or B, depending on either of the two, if they want the key to use it for communication with the other party. All right, so that's what the protocol is. So now we move on to study the non-repudiation properties of this protocol. Okay, so first of all, we're looking at non-repudiation, what we call non-repudiation of origin. Okay, so the idea here that we would like, or let's say B would like to prove that A indeed sent message M. Okay, so the non-repudiation in this case is revolving around whether you have sent or received message M in this protocol. Okay, so this is what you would like to prove, and you can think of this message M, for example, as the receipt for a certain transaction. Okay, so some kind of financial transaction or business transaction that you perform, and M can, in this case, sort of as an example, be, let's say, the receipt for that financial transaction. So the first thing B would like to do is to prove that A indeed sent that message M, or in other words, that the transaction actually did come from A. Okay, so what does B need to do in order for it to prove to the outside world or to some kind of external arbitrator that A indeed did send M and it wasn't someone else who sent M? Okay, so B has a couple of information here from its participation in the protocol. So first of all, note that B received a message signed by A. Okay. However, remember that at that stage, B did not have the key K. Okay, so B can't really read M in this case, because M is encrypted with K. However, later on, towards the end, remember that B was able to retrieve the key K using this specific signed message from the server. Okay, so this is essentially this last message over here. And basically, it's got these two pieces of information. Okay, so now the idea is can B prove using a combination of these two pieces of data, can it prove to the external environment that A indeed sent the message M, then it wasn't someone else? Okay, so the answer is as follows, or the reasoning is as follows. So first of all, you have the first data. Okay, so if you look at the first data, the implication that B can arrive to is basically that A sent this encrypted message M. Okay, and that's very simple to prove because A has signed the whole thing. So A is basically attesting to the fact that it wants to send, or that it is the one who sent this encrypted message M to B. So that's the first piece of evidence, okay, or the first kind of conclusion. On the other hand, in the second conclusion, we can essentially state that that A also sent the key K, and that is because simply the server here is attesting to the fact that this key is a key which is used for communications between A and B. Okay, so as a result, we can conclude that it was indeed A who sent the key K to the server. And that's also by virtue of the fact that the protocol tells us so. Okay, so as you can see in the protocol in message 3, it is A who deposits this key at the server. Okay, so therefore, if the server is able to distribute the key, it means the server was happy that this key indeed came from A. Okay. So as a result of the second piece of data, B is able to conclude that A sent the key K. However, if A sent the key K and A sent the encryption of the message M with the key K, then obviously the combination of these two pieces of evidence is that A must have sent M. Okay, so if you have the key and you have a message that is encrypted with that key, then that proves that you also have the message itself. Of course, here the assumption that we're making is that it's the key is a symmetric key, of course. And on that basis, we can conclude, or B can conclude, that A sent the message M. So that's the first property, or what we call non-repudiation of origin, and that is a property that serves or helps B's cause. Okay. Now there is the opposite kind of property, which is called non-repudiation of receipt, and as we said, in this case, we would like to prove that the other party, and in this case B, indeed did receive the message M. Okay, so what do we do in order for us to prove that, or in order for A to prove that? Well, A has also a couple of data. First of all, it's got the second message that it received from B, which was essentially signing the encrypted message. Okay. And the other thing that A has is, same like in B's case, is the key that it was deposited at the server, and that key has been distributed in the last message by the server, in this case for A. Okay. So in this case, using these two pieces of data, A will try to essentially prove that B indeed did receive the message M. So how does it conclude that? Again, following the same kind of line of reasoning that we did for the first case. In this case as well, we have, first of all, we can show that B has indeed received the encrypted message M, and that is coming from the first piece of data. Very simply, if you look at it, or in an intuitive way, you can see that B is sending the encrypted message back to A. So that means that B has this encrypted message M, or has indeed received it already. Okay, it doesn't prove that it has M, but it proves that it has the encryption of M using K. From the second piece of data, it proves that indeed B has got K. Okay, so again, remember that the server is saying to A that here is the key that you can use for communication with B. But if the server is able to perform this message here, the server is also able to perform this other message here. So in other words, the symmetry of this event can allow A to conclude that B equally has got access to the key K. So as a result of these two conclusions, that B has got access to the encryption of M using K, and that B has got access to K, it immediately follows that also B has got access to M. Okay, so if you have access to an encrypted message and the key that was used in its encryption, again assuming it's a symmetric key encryption, you also, or the assumption is that you also have access to the message itself. So in this case, both parties have managed to prove to themselves or to any other external arbitrator that the other party has was either the party that sent the message M or the party that received that message M. And you can imagine here, as I said earlier, that M can be anything in the world. It could be a financial transaction, some kind of a receipt, some kind of proof of an evidence, or anything else that your business application requires it to be. So this protocol gives us non-repudiation with respect to this message M for both parties participating in the protocol. It also is a fair protocol, okay, and in this case we need to sort of define why is it fair. What do we mean by the word fairness? Remember, as I said at the beginning, fairness means that you cannot produce evidence earlier, okay, before the other party can. Okay, so this is a very important property because you don't want to terminate the protocol somewhere in the middle and then go and make a claim that indeed you're entitled to certain things, whereas the other party was not able to actually complete the protocol run with yourself, and it's so therefore it doesn't become a fair communication. Okay, so the way we do that, or to sort of test this fairness, is by dividing the protocol or giving it a timeline. Okay, so we can divide the various events according to to whether or at what point of time they occurred, and in this case we don't need to have an absolute measure of time. We can just assume some kind of a relative relative clock. Okay, so if we started at point zero, and point zero is before anything has happened, that is the first point in our timeline, at which case nothing has happened yet. And then if we move to the first tick, or the first unit of time, that will be the point of time which splits or happens right after the first communication event and just before the second communication event. And then the second point of time is right after the second event has completed and just before the third event starts, and so on. Okay, so you can see here the last point in time is when everything has taken, or that has happened or taken place. Okay, and these, of course, the last two events, as we said, they're basically simultaneous. They can happen in parallel, and therefore we treat them as being sort of causally independent from each other. Okay, so they, you know, they can happen in any order or in parallel. It doesn't matter. We are in this case treating them both as being simultaneous events. So in order for you to convince yourself that this protocol is fair, I would like you to offline look at essentially each point in time, and try to understand what each of these two agents has got in terms of the messages or the data that it obtained, and then try to convince yourself that unless you reach point 4, in which both of these two events have taken place, the protocol is not going to provide any repudiation for either side. Okay, so up until point 3, you cannot prove non-repudiation for either, in terms of the message M, for either A or B. And then you really have to wait until point 4 here, that either side can essentially reach that conclusion. So that was all in terms of non-repudiation. We took a simple example, but of course there are lots of examples in literature. So if you want to sort of try to get more detail, um, try to go more in depth in this topic, there is a lot of literature on non-repudiation, and particularly on non-repudiation protocols, and it essentially, as I said, they form an important basis for systems like e-voting, and all these sort of auditing and accountability systems, if they include some sort of communication element in them. Now we move to the second class, which in this lecture, and that is a quite a relevant class to non-repudiation. It's called anonymity. Okay, so anonymity really is the opposite of, almost the opposite of non-repudiation, because in this case, what you're trying to do is you're trying to participate in a protocol and come out of it completely anonymous. Okay, or that certain events were anonymous in the protocol. Okay. In this case, that equates to the statement that the environment has no way of identifying who originated those events, and if the events are related to the identity of the participants, that identity remains anonymous all the way through until the end of the protocol. So again, in fact, anonymity protocols have also are important, and the anonymity property is important in things like e-voting systems, because you would want to essentially participate in the e-voting system without being identified, okay, or without your decision being linked to your identity. So in this case, the setup is again slightly different because you do have an observing environment which is trying to understand what's going on in the protocol. But what you want to really do is you want to essentially give that environment a set of events which are completely anonymous or anonymized, whereas the actual events that do take place in the protocol itself, essentially they're hidden or shielded from this observing environment. So in fact, in this case, you can think of the protocol as having two layers: the actual protocol with all the nitty-gritty stuff that goes on within it, and a protocol as a system that can be observed by the environment. And that's where essentially you would want your events to be completely anonymized. In other words, you cannot identify who has performed what in the protocol at that level. As I said, really anonymity is about breaking this kind of link between the agent and the event or the message, okay, or indeed that link must remain secret, and it must not be known that this agent performed or a certain event, for example, sending or receiving of a message, or that message indeed is coming from a certain agent. Okay, so that relationship needs to always remain secret. So the best way to explain how anonymity protocols work is through going through a famous example, and that's the example of what we call the dining cryptographers problem. So the idea of the dining cryptographers problem is that you have three cryptographers. So this is like a thought experiment. Okay, so you have three cryptographers who went to a restaurant. First of all, they work at an organization, and then one day they had enough and they decided to go out for a dinner meal at a restaurant. And at the end of the meal, each cryptographer was informed by the organization secretly whether or not he or she would be paying for the meal. Now, towards the end, either at most one will pay or the organization will pay for the dinner. So the idea is that they go out for a meal. At the end, they decide whether one of them is going to pay for the meal and not claim the expenses, or that they will decide that their organization or employer will be the one paying for the meal instead. So the goal of this dining cryptographers protocol then is that one of them, as I said, pays, or the organization pays. However, it's very important that if it is one of them who pays for the meal, that the identity of that cryptographer or of that paying cryptographer remains secret or anonymous. Okay, so it's either the organization who pays or a cryptographer, and if it is the cryptographer, that the identity of the cryptographer must remain secret or anonymous. So let's look at a little bit more kind of detail into how the protocol works from a conceptual point of view. So in this case, you have the three cryptographers A, B, and C. And in this setup, they all share some kind of a message. So each pair of them shares a message between them. Okay, so A shares a message with C called M1. C shares a message with B called M3, and B shares a message with A called M2. So essentially A knows about M1 and M2, B knows about M2 and M3, and C knows about M1 and M3, and that's the knowledge they have. Now, at the end of the meal, each cryptographer will make an announcement. Okay, so the announcement here is very important because it's taking us to this level. Okay, so essentially, an announcement is this kind of event which you're essentially um, announcing to the external environment. Okay, so each cryptographer will make an announcement, and that announcement essentially is the XORing, okay, of the two messages that it knows about. Okay, so A1 will XOR M1 and M2, C will XOR M1 and M3, and B will XOR M2 and M3. And if you don't know what XOR is, I urge you to check it out on Wikipedia. It's a logical operation which returns 1 if the two digits or 2 bits are different, and it returns 0 if they are the same. Okay, so 1 XOR 1 is 0, 0 XOR 0 is 0, and 1 XOR 0 is 1, and 0 XOR 1 is 1. Okay, so that's just in short. So the announcement will be, if it did not pay, if that cryptographer did not pay for the meal, they will just announce the XORing of the two messages that they know about. On the other hand, if the cryptographer did pay for the meal, then they will flip the result or announce the inverse or the negative of the result. Okay, so notice the not here, or the negation of the result of XORing these two messages that they know about. And the set of the events that then are produced to the external environment is the three announcements made by A, B, and C. Now, moving on, and in this case, we're assuming here that these messages are just 0 and 1. Okay. The In this case, the environment then is going to calculate or use an algorithm to decide whether it knows that one of the cryptographers paid or did not pay. Okay, so what is this algorithm? The algorithm is very simple. It takes the three announcements and it XORs them with one another. Now, if the result of the XORing of the three announcements was an even number of ones, then that means that basically the organization has paid the bill. On the other hand, if the XORing was an odd number of ones, then that implies that one of the cryptographers paid the bill for the dinner. However, notice here that even though you will arrive at that conclusion, you have no way of determining the identity of the cryptographer that paid the bill. Okay, so you only know there was one of the cryptographers who paid the bill, but you have absolutely no way of knowing which cryptographer actually paid the bill. So here is a concrete example, and in this case we have on the left hand side the three cryptographers, and they didn't pay. It was the organization who paid. So A shares the digit 1 with B, and 0 with C, whereas B shares again that number 1 with A, and number 1 with C. whereas C, of course, shares 0 with A and 1 with B. So we said that in the case that none of the cryptographers pays, they will, all of them, they will just XOR the 2 bits they know about and announce the result without lying about it. Okay, so A will XOR 0 and 1, which is equal to 1. B will XOR 1 and 1, which is equal to 0, and C will XOR 0 and 1, which is equal to 1. And the announcement that A, B, and C will make are respectively 1, 0, and 1. Now, of course, notice here that by making this announcement, you don't know, or you do not reveal what, or the environment cannot reveal what these secret digits or secret shared messages were in the first hand. Okay, so all what the environment can observe is the 3 announcements, the 3 results of the XORing operations. It has no way of knowing what that message was, what that message was, and what that message was. Okay. So once it did receive the 3 announcements, or once the environment essentially obtains these 3 results, it will then perform this operation here, which XORs those 3 results, and 1 XOR 1 XOR 0 is equal to 0, which is an even number of ones, which basically means that the organization has paid for the dinner. On the right hand side example, you have here A paying for the dinner. So A decides that they don't want to burden the organization, and they will just basically fill the bill from their own pocket. And in this case, A will lie about the result of the XORing. Okay, so instead of announcing 1, it will reverse that result and announce 0. On the other hand, B and C will essentially not lie. They will say the truth because they didn't pay. So they will just XOR their secret digits and announce the result just as it is. Again, notice here that the observing environment, or the external observer, again has no way of telling that A is lying, because simply the external observer has no access to these 2 numbers that A shares with B and C. And so therefore, if A says the result is 0 or 1, whatever it wants to say, the external observer has no way of determining that that was a lie or that was, not a lie. So all what the observer can do is it can take the result of the announcements. Okay, so in this case, the 0 from A, 0 from B, and 1 from C, and XOR these 3 results, and the outcome will be 1, which is an odd number of ones. So because it's an odd number of ones, the observer will conclude that one of the cryptographers paid for the meal, but it has absolutely no way of knowing that it was A who paid for the meal, simply because it has no way of knowing which one of these 3 cryptographers is actually lying, okay, about the result of the XOR, and therefore, in other words, they are the ones who have paid for the meal. And you can try for yourself various combinations of these secret messages, just to have different variations on this example, and so that you convince yourself that you understand how it works. But always remember that it's all only one cryptographer who pays for the meal. Okay, so if you attempt here to, let's say, flip also the result of B, then you will reach at a wrong conclusion, and you're basically using the protocol in an incorrect way. So always remember that what the protocol gives you is the knowledge that either the organization paid or one cryptographer paid, but you have no way of knowing the identity of that cryptographer. That's all for this week. Thank you very much for listening. Bye bye.